Welcome back to another session of Physical Sciences. As you know, when you see me, I'm doing chemistry. And today I'm going to go on with chemical equilibrium, and we specifically going to work and look at Le Chatelier, the Frenchman. We will look at his principle, Le Chatelier's principle and chemical equilibrium. So what we've done to date is we spoke about the definition of chemical equilibrium and dynamic equilibrium. We connected that to graphs. We did Kc calculations and Kc expression. And what we're going to do today is, like I said, we're going to look at the Frenchman's work, Le Chatelier, and we're going to look at his principle and how that links up to the equilibrium in chemical equilibrium. The terminology is Le Chatelier's principle, which we will shortly define. We're going to talk a lot about disturbance, or sometimes we will refer to this disturbance as the stress, seeing that the stress is what's going to happen at equilibrium after equilibrium has been reached. And then we're going to talk a lot about the word favored. And when we look at equilibrium, chemical equilibrium, we know that it must happen in a closed system, and it should always be a reversible reaction. So with the reversible reaction, we're also going to talk a lot about our delta H, or our enthalpy, and we will also refer to this a lot as we work further with Le Chatelier's principle and chemical equilibrium. The definition of chemical equilibrium, again, just to refresh your memory, it is a dynamic equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. For a reversible reaction, and we remember it is in a closed system, the closed system means there's no interaction with the surroundings. Just want to take you back to the rate graph where we spoke about the rates of the reaction. We specifically looked at the rate of my forward reaction and the rate of my reverse reaction as we work up to a chemical equilibrium in a reversible reaction that is in a closed system. So we looked last time that our rate is fast at the beginning, slowing down for the forward reaction, and slow down, and then at this point remains the same. For the reverse reaction at the beginning, there's no product, and as soon as it starts to get product, the rate becomes faster and faster until a point where these two lines are basically parallel, and at that line or that point, the rate of the forward reaction is equal to the rate of the reverse reaction. We looked at this earlier when we spoke about the overall reaction for the preparation of ammonia gas. When we look at the concentrations again, just a refresher on concentrations. Remember, for the concentrations, we had 3 moles of hydrogen gas, 1 mole of nitrogen gas that produced 2 moles of ammonia gas. And we showed that in the beginning, the concentration of the nitrogen decreased, the concentration of the hydrogen decreased, and the concentration of our ammonium increased. I want you to see that our nitrogen decreases, but hydrogen decreases more. You can see on the slope that it's a bit steeper for hydrogen. The reason for that is they react in the ratio of 3:1. Then we come to Le Chatelier. What did Le Chatelier say about disturbance of that equilibrium? When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. Oh, that's a lot that we've said. It must be in a closed system. It will reinstate the equilibrium by favoring the reaction that oppose the disturbance. The factors that will disturb the equilibrium is 3 factors that can disturb equilibrium. That is concentration. Remember we said the square brackets. Then we have pressure. Remember that pressure works hand in hand with your volume. So a change in volume can change or alter your pressure. And then the third one is temperature. When we look at Le Chatelier, we will have to have a way of answering Le Chatelier's questions, or we use Le Chatelier's principle to answer questions after equilibrium has been disturbed. So the first thing will always be to identify the stress. So we use the S. Remember that stress is actually the same as your disturbance. Then we will state how the system will respond to it and which reaction will be favored. Just before we go on, I want to explain to you what does it mean for a reaction to be favored. When a reaction is favored, it does not mean or indicate that the reaction happens faster than earlier. But favored means that the reaction happens faster than the reaction in the opposite direction. So if I say the forward reaction is favored, then I basically say the forward reaction happens faster than the reverse reaction. It's important to understand that. Right. And just to go on again, answering questions on Le Chatelier, the first thing, as I said, to identify the stress. When we know the stress, then we will respond and look at the response from Le Chatelier, which we call the R. Then which reaction is favored, we will use an F to remind us, and then the effect after the new equilibrium is established is our E. So instead of saying that is safe, when we answer questions on Le Chatelier or equilibrium, we will use, I want to say, we will use SREF method, S-R-F-E. And that brings us to the point where I think we all need now. Please come back refreshed. Welcome back from the break. I hope you're ready. In the previous session, we looked at Le Chatelier, what the principle says, and how to answer questions if we will do chemical equilibrium and when the equilibrium is disturbed. I would now like us to go into this session where we will now use Le Chatelier and look at the factors that change the equilibrium and also then show the S-R-F-E that we spoke about in the previous section. Remember, the S is for the stress, the R is the response, the F is which side or which reaction will be favored, and the E is the effect after equilibrium. So when we're going to apply Le Chatelier's principle, we must remember that we always start in a closed system, and the closed system is normally in chemical equilibrium. If the system is not in chemical equilibrium, we cannot apply Le Chatelier's principle. So Le Chatelier actually only comes in when a system has reached equilibrium and there is a stress on the system. So we will apply the stress to the system, and the first one that we will apply is the concentration. Right. So my stress here is an increase in concentration. Now what I'm going to do is I want us to work with an hypothetical reaction, and we need to now remember everything that we've done up to now in terms of using our balanced equation for Kc expression. Right. So we have 3A, 2Bs. I want you to note that my 2B is a solid. Then I've got 2C that's forming and 1D that's forming. I just want to remind you that this coefficients here becomes our exponents in Kc. And I just want to remind you again that when we work on the Kc on the constant, the equilibrium constant, we do not use liquid and solid as part of our expression. What's important now is this is a reversible reaction, and this delta H is negative is for our forward reaction. Please remember the enthalpy that's given on a reversible reaction always apply to the forward reaction, meaning the opposite is true for the reverse reaction. In this case, we have the enthalpy to be negative, meaning that my forward reaction is an exothermic reaction. And if my forward reaction is exothermic, then it basically means that my reverse reaction is endothermic. Right. The question is, what will happen if more A is added to the closed system? Now, if more A is added to the closed system, it basically means that the concentration of A is increased. Now, you are not supposed to use little arrows up and down as I do now. You need to write the words that the concentration of A is increased. Right. So now we're going to use our SRFE to explain what's happening. So, what is the stress? The stress for this system is an increase in the concentration of A, and according to Le Chatelier, the system reacts to decrease the concentration of A. Now, for the system to do that, it means it needs to use up A. And for it to use up A, it means it must use A to make more of C and D. What you need to realize is you need both A and B to make C and D. So what's going to happen now, the effect is we're going to now favor the forward reaction, because it's in favoring the forward reaction that we can get rid of this high concentration of A. A will be used to make more of C and D, so the effect will be that the concentration of D and C will increase. This is the effect after equilibrium. What will happen to Kc? Kc will remain constant. Why does it remain constant? Remember, Kc is only affected by temperature. Now we will look at another stress. Again, an increase in a concentration, but this time we will increase the product. So, what will happen if more C is added to the closed system? For starters, that will mean that my concentration of C will increase. What is the stress? The stress is a concentration of C that will increase. What will the system do according to Le Chatelier? The response will be the system will react to try to decrease the concentration of C. How will the system do that? Whenever you want to decrease a concentration, you need to use up some of that substance to decrease the concentration. So if we want to use some of C, then it basically means that we will favor the reverse reaction. And when the reverse reaction is favored, it means after equilibrium we will have more of A and we will have less of D. Why do we have less of D? Because when we had to use up C, we needed to use D to make A and B. So please keep that in mind. Right. What will happen if A is removed? Now, when we use the words A is removed, it doesn't mean that we're now going to take A and there's no more A. No, it just means that we take some of A out of the system. So what will happen? Firstly, your stress is a decrease in the concentration of A. What does that mean? That means the system now, to reinstate the equilibrium, the system will have to make more A. So the stress is a decrease in the concentration of A. the system will react and try to increase. So how will the system get more of the substance? It means that the system will have to make more of A. How will we make more of A? We need to now favor the reverse reaction. Because if we favor the reverse reaction, we will use C and D now to make more A. And if we have more A, we need to remember we've used C and D now, so the concentration of C and D will decrease after equilibrium is reinstated. That's the effect after the equilibrium. What will happen to Kc? Kc is only affected by temperature, so Kc will remain constant. This is a very important one, and this is one that they trick us in the exam where we make a mistake, an honest mistake. So the question is, what will happen if B is added? Now what we need to remember is B is a solid, and a solid does not take part in this equilibrium, so it will not have an effect on anything for the equilibrium. So the equilibrium is only affected by aqueous and gases. It's not affected by liquids and solids. This is important for you to remember. So the next one that we will look at is what will happen if we start in a closed system and the system is in chemical equilibrium. What will happen if we apply a stress to the system, but this time we apply pressure? Now we spoke about pressure at an earlier stage when we spoke about the rates of reaction. We also said that pressure is inversely proportional to the volume. So as soon as there's a change in volume, it will affect our pressure. Pressure can only be affected in gases. It's only in gases that we get pressure. Just a reminder again, the pressure is affected by the change in volume. So if the volume is decreased and the number of moles remain the same, then it basically means that in this decreased volume, my increase there will be more. My pressure will then be increased. So what happened now is that number of moles is now in a smaller space, is confined to a smaller space. There's more collisions per unit time, and there's more effective collisions per unit time. So it will obviously increase the rate. But what we need to know is that a decrease in volume will increase our pressure. So we know that pressure is affected by the volume. As we said, an increase in volume will decrease the pressure, and a decrease in volume will increase the pressure. Right, a decrease in volume will increase the pressure. That is, the question now is, what will happen if the volume of the container is decreased? Right. You should now have in mind that the volume is inversely proportional to the pressure. An increase in pressure favors the reaction that produces the least number of moles. So when the volume is affected, when the volume is decreased, then if you look at C is equal to N over V, then it basically means that the system will try to make less number of moles. What's very important when we look at pressure is we need to go add the number of moles on both our reactant and our product side. Just remember, the solid is not part of our Kc expression. So on my left-hand side for my reactants, I have 2 moles. And on my right-hand side, I have 2 plus 1, which is 3 moles. So let's go look at what Schreif says. The disturbance or the stress was an increase in pressure. Remember, the volume was decreased. So the system's response is to react to lower the pressure by forming less number of moles of gas. So for us to have that, our least number of moles is this side, because this side we have 3. So the reverse reaction will be favored. And if the reverse reaction is favored, it means we will use C and D to make more of A. So Kc will remain the same. Kc is only affected by temperature. Now we move on to the third one, the third factor. There's only 3 factors that we're going to study, where we're going to look at what the effect of that disturbance will do. We've looked at concentration, we've looked at pressure, and now we are quickly going to look at temperature. Right, an increase in temperature always favors the endothermic reaction. The endothermic reaction is the reaction that uses or absorbs the energy. Secondly, a decrease in temperature will always favor the exothermic reaction. The exothermic reaction is again the reaction that produces energy. Remember, a change in temperature has got an effect on our Kc value. What you need to know is this is something that you need to study. Increase in temperature favors the endothermic. Decrease in temperature favors the exothermic reaction. Right. What will happen if the temperature is increased? Now we know the forward reaction in this case is exothermic, meaning that my reverse reaction, as I said earlier, is endothermic. So what will happen now is the forward reaction is our delta H, but because there is an increase in temperature, it will favor the endothermic reaction. So how will we answer it? The stress is an increase in temperature. What does an increase in temperature mean? That it will favor the endothermic reaction, the one that uses the energy. And in this case, it is my reverse reaction. So the system will react to try to decrease the temperature by favoring the endothermic reaction, in this case, as I said, the reverse reaction. And what will the effect be on C and D? If we favor the reverse reaction, it means that we will use C and D and it will make more of A. Now, if we go and look at the increase of A and the decrease of C and D, and we link that and substitute that into Kc, we see our numerator is smaller than our denominator, meaning that Kc will have a value smaller than 1. And that brings us to the end of this session. Thank you for your time. Welcome to another session of physical sciences, specifically chemistry and specifically chemical equilibrium. The last time we worked and we learned about Le Chatelier's principle, and we spoke about Le Chatelier's principle. We looked at the factors, and we also looked at how to answer these questions on Le Chatelier's, when there's disturbances, how to answer these questions. And we said that we have the SRFE way of answering it. In this session, I would like us to look at graphs. I specifically want us to look at concentration graphs. And this concentration graphs is now linked to Le Chatelier's principle. When a stress is applied to a closed system in a state of chemical equilibrium, remember this stress must be applied where there's chemical equilibrium, what changes will be seen on the graph of a concentration versus time graph? So we've seen the rate graphs a little earlier. We spoke about the changes in the rate of your forward and your reverse reaction. But whilst we were looking at the rate graphs, I also brought up for the example of the production of ammonia, I also showed you how it will look if we look at the concentration of the different substances that are used. So this session will basically focus on how does the concentration time graphs look. We're going to investigate the changes to the concentration versus time graphs, and a closed container contains a mixture of hydrogen, nitrogen, and ammonia at this 350 Kelvin at a specific temperature. The reaction mixture has reached a state of chemical equilibrium. Now, we have in front of us the concentration graph that I showed to you before. Remember what we said? This is the nitrogen, the purple line. We have a yellow line, which is the hydrogen gas, and then the ammonia is the red one. Just remember, this is a concentration graph, so it will look at the different concentrations of the substances. The concentration of the reactants and the products at this point from the white line onward, these concentrations are constant. Remember, I said to you last time, we don't say the concentrations are the same because it's not necessarily the same. It's actually never really the same, but the concentration remains constant at that state of chemical equilibrium. The factors that will disturb equilibrium, we've learned about them according to Le Chatelier. We've got concentration, we have pressure in the case of gases, and then we will look at the change in temperature, how that will affect the concentrations and how it will affect the concentration time graphs. A closed container contains a mixture of nitrogen, hydrogen, and ammonia at 350 Kelvin. The reaction mixture has reached a state of chemical equilibrium. Remember what I said last time? There must be a state of chemical equilibrium, else the equilibrium cannot be disturbed. So, in this case, the concentration of hydrogen is increased. Now, what you should think about is the disturbance is an increase in hydrogen gas. When we look at the graph in front of us, firstly, I need you to note that the fact that we have parallel or horizontal lines here, you need to understand that at that point where my nitrogen, my hydrogen, and my ammonia has got horizontal lines horizontal to the time axis, it means at that point the system is in chemical equilibrium. Then comes the disturbance. And what is the disturbance? An increase in hydrogen. So our hydrogen concentration increases. So what will happen to the rest of the system? Let's see what Schriff shows us. There's an increase in the hydrogen concentration. What did Le Chatelier say? That the system will react to decrease the hydrogen gas. And for it to decrease the hydrogen gas, it must use up the hydrogen gas. And in using up the hydrogen gas, it actually means that the hydrogen and nitrogen must now favor the forward reaction. And when the forward reaction is favored, we will have less of N2 because the N2 plus the H2 has now increased the concentration of the ammonia. Now we're back at the graph, the concentration versus time graph. Remember what we said. We said that the disturbance was an increase in hydrogen gas. What did the system do? The system tried to decrease the hydrogen gas. And in decreasing the hydrogen gas, the forward reaction was favored. When the forward reaction was favored, the concentration of the ammonia gas was increased. So we have a vertical line up to show the disturbance, and we use a vertical line up for an increase in concentration. Then we see that the product is now increasing with a curved line, and the nitrogen gas that's now being used with the hydrogen to use the hydrogen gas up, the nitrogen will now decrease, and ultimately hydrogen will also decrease, and it will go into a new state where we have horizontal lines that's parallel, and that means that the concentration here is now constant. Remember, we do not say the concentration is the same, we say that the concentration is constant. Right. That line there just shows us that from there onward, our concentration is the same. Meaning, this is the new equilibrium that's being reinstated according to Le Chatelier. Now, we're going to just quickly summarize what just happened on the concentration graph when one of the concentrations is increased or decreased. Specifically, we looked at an increase in concentration. When we have an increase in concentration, the feature on your concentration time graphs is there's one vertical line. And because it was an increase, that one vertical line for hydrogen gas went up because it showed increase. The other two was affected by the response of Le Chatelier, and they were more curved lines. If we would have worked with a decrease in concentration, we would have had one vertical line, but that one vertical line would have been down. We've now looked at the disturbance of the concentration of one of our reactants, and we looked at how that is shown on a concentration time graph after the disturbance to reinstate the equilibrium. Now we're going to look at the next one. We're going to look at pressure. Remember, pressure is we only get pressure in gases. And whenever I say the word pressure, you should think volume. So we still have the nitrogen, hydrogen, and ammonia gas at the same temperature there. The reaction is at a state of chemical equilibrium, and the disturbance now is the volume of the container is decreased. What does the volume, if we decrease the volume, what does that do? Right, a decrease in volume will now increase the pressure. Remember, our volume is inversely proportional to pressure, or our pressure is inversely proportional to volume. So the decrease in volume leads to an increase in pressure and the increase in concentration for all the gases. So whilst the volume was decreased, the pressure was increased and the concentration of all the gases was increased for that specific volume. Right. Here we have our concentration time graph, and remember we have concentrations of ammonia, nitrogen, and hydrogen. First thing here is, when we look at the disturbance of pressure, you will see there's a spike for each one of them. Just want to take you back. Remember, we said there will be an increase in pressure, and that will increase the concentration for all gases. So it increases the nitrogen, the hydrogen, the yellow one, and it increases the ammonia. What do we know about an increase in pressure? The stress is an increase in pressure, and according to Le Chatelier, the system will react to try to decrease the pressure by decreasing the number of moles. When we want to go for the number of moles, remember we're working with pressure. We have 2 moles on the right-hand side and 4 moles on the left-hand side. So if we want to decrease the number of moles, the reaction that produces less number of moles will be favored. In this case, it is the forward reaction. So what will happen if the forward reaction is favored? It basically means that the concentration of nitrogen and hydrogen will decrease, and the concentration of ammonia will increase. So the nitrogen and hydrogen will decrease, and the ammonia will increase. So here we show the disturbance, our vertical lines. The pressure was increased, so all the vertical lines were up. And now, after equilibrium, we have more NH3, we have less N2, and even less H2. Remember I said to you earlier, there's more of a decline in the hydrogen gas because our nitrogen to hydrogen is in a ratio of 1:3 in this reaction. Right. When we look at the stress of change in pressure, the feature on the concentration time graphs, there's always many vertical lines. If the pressure is increased, those vertical lines will be up. If the pressure is decreased, the vertical lines will be down. And then only we show the effect of equilibrium. That brings us to the last one, where we're going to look at the effect of temperature, and we're specifically going to look at the effect of temperature in a closed system that is in a state of chemical equilibrium. We will look at the reaction of hydrogen, nitrogen, and ammonia at 350 Kelvin. The reaction mixture has reached a state of chemical equilibrium, and we want to now work out what will happen if the temperature is increased. Now we know, firstly, when we talk about temperature, we first need to go look at exo and endothermic reaction, because an increase in temperature will always favor the endothermic reaction. So we need to go see which reaction here is endothermic, and we see that the forward reaction is exothermic, meaning that the reverse reaction is endothermic. An increase in temperature will then favor the reverse reaction, which in this case is endothermic. Or we can say an increase in temperature favors the endothermic reaction, which in this case is the reverse reaction. What is the stress? According to Le Chatelier, it's an increase in temperature. The system will react to decrease the temperature by favoring the endothermic reaction. In this case, our endothermic reaction is the reverse reaction, meaning we will have less of NH3 and more of N2 and H2. How will that look on our graph? On our graph, we will see our NH is used up, our N2 is becoming more, and our H2 also becomes more. Remember, we have a 1:3 ratio. But what you need to note here is we only have curved lines when we look at a temperature as a disturbance. So, the feature on your concentration versus time graph is all lines are curved. We will see that an increase in temperature will show that the concentration of your endothermic reaction increases. Decrease in temperature, the concentration of your products of your exothermic reaction will increase. And that brings us to the lovely part of the day. We're going to take a break, and I'll see you soon. Welcome back from the break. I'm glad that you could join me again. We're going to go on with graphs, but this time we're going to look at the rate of the reaction graphs for Le Chatelier versus time. In our previous session, we looked at the concentration versus time. We will now look at the rate versus time. When a stress is applied to a closed system at a state of chemical equilibrium, what changes will be seen on the graph of the rate of reaction versus time? Now we're going to investigate the same reaction of nitrogen, hydrogen and ammonia, where ammonia is being produced at a temperature of 350 Kelvin. The system is in chemical equilibrium, and now what we need to remember from rate of reaction graphs is, we've dealt with this graph a little earlier, that we said in the beginning it will be fast, nothing, become a bit faster, slower, until a point where the rate of our forward reaction is equal to the rate of the reverse reaction. At this point, we are at chemical, or the system is at chemical equilibrium. Just a little reminder again, when we spoke about rates a few sessions ago, we said that the rate of a reaction can be affected by 6 different factors. We also spoke about the collision theory and how these factors specifically have an influence on the rate. Just as a reminder, we looked at concentration, we looked at surface area, pressure, temperature, addition of a positive catalyst, and also the nature of our substances. Now what we are going to do now is we're going to look at some examples where we will look at the rate graphs for some of these factors. We're still in the closed system and we're still busy making ammonia at 350 Kelvin, and it is at chemical equilibrium. The question here is, a catalyst is added to the reaction mixture. Catalyst, I just want to say there it's a positive catalyst. We know that a catalyst is a substance that does not take part in the reaction, but it lowers the activation energy. Okay, so what will happen to the rate of the reaction? Now when we add a catalyst, we actually speed up the reaction. So which reaction is sped up? The forward or the reverse reaction? Right. When we put or add a catalyst, there is an increase in both the rate of the forward as well as the reverse reaction. But there is no change in the concentration. Remember I said in an earlier session, the product is formed faster, but the amount of product that forms remains the same. When we look at the rate of the reaction for nitrogen, hydrogen, and the producing of ammonia, we can see that the rate of reaction goes into chemical equilibrium, and when it's now in equilibrium, it's being disturbed by a catalyst. What will happen? Because it's a positive catalyst, it actually speeds up both the reactants, but nothing else will happen. It speeds it up and it goes to a new equilibrium position. When we look at your concentration graph for a catalyst, you can see after disturbance, your concentration graph actually shows that all your concentrations remained the same, constant. Right, now we want to look at the increase in temperature. Now, we are now increasing the temperature to, let's say, 400 Kelvin. An increase in temperature, the rate of the forward and the reverse reaction will both increase initially the rate of the endothermic reaction will increase more, because it's actually your endothermic reaction that's being favored. But take note, both of the rates will increase at first. When we look at the rate of reaction versus time graph, we can see there's a spike for both the forward reaction as well as the reverse reaction. But the spike for the reverse reaction is bigger because the reverse reaction is the endothermic reaction and the forward reaction is the exothermic reaction. With an increase in temperature, the reverse reaction, being endothermic, was the reaction that was favored. The next one that we're going to look at is an increase in the hydrogen concentration. When we look at an increase in the hydrogen concentration, it is an increase of a reactant. The rate of the forward reaction increases, and it will increase sharply because it will then start to decrease. There was now a lot more hydrogen in the system. What will happen to the rate of the reverse reaction? It will increase slowly. If we look at the rate versus time graph for that increase in hydrogen, we can see because it was an increase in hydrogen and the forward reaction was favored, the spike for our forward reaction is high, no spike for the reverse reaction, but the forward reaction then starts to decrease, and then the reverse reaction starts to increase. When we go look at the features of your rate of reaction graphs, with the addition of a positive catalyst, we had two vertical lines to show that there was an increase. Then we looked at a change in temperature, specifically an increase in temperature, two vertical lines with different lengths. The endothermic was longer because the endothermic was the one favored. Change in concentration, one vertical line, and the other one was a curve. To summarize, remember you must learn your Le Chatelier's principle off by heart. They like to ask that one in the exam. You must recall the factors that will affect the chemical equilibrium. Remember, we have 3 of those. Practice using the answering method that we explained to you today, and only temperature affects the Kc. Recognize how a stress is applied to a system when it's in chemical equilibrium and how that will affect the concentration and the rate versus time graphs. Remember, it's 2 different graphs. This is where we will end our session of today. I would like to thank you for participating. Have a good one.